This drill is going to be the classification drill. So what we're going to do is I've got this problem here, and I'm not going to try to answer it, but I'm going to try to classify which one of these topics it was, and then I'll give the opening move. So let's give it a shot. So a point charge Q is located at a distance d from the center of a grounded conducting sphere. The radius r, d is r, something like this. There's Q, it's distance d. This is a grounded conducting sphere, radius r, so v equals 0, and b is less than r, so it's actually a bit closer. No, d is greater than r, so just move it up here. So determine the potential everywhere outside the sphere and the induced surface charge density. Um, so which one of these topics was it? Um, I'm guessing it's probably going to have a couple different ones together. So it looks like we need electric potential and conductors. Uh, Probably Laplace equation. No, because we have a charge, so it would be the Poisson equation. Method of images. Is that it? And for the opening move, I think first we put the image charge inside. Although I'm not too sure because the D is greater than R, so it might not actually work that way, but maybe. So we'll first put the image charge inside, then we use the Maxwell boundary. Well, first we would have to use Gauss's law for electric fields. Or maybe we can jump straight to find the surface charge, then possibly use the mm, spherical solution of the Gauss equation. I don't know. This is okay. So we just have to solve Laplace equations. We get this type of thing, which is fine. That makes sense. So it automatically satisfies Laplace equations. I didn't actually realize that. So let me just mark that the method of images automatically automatically satisfy loss. That's kind of interesting. That the potential is known. Yeah, this is the Maxwell surface. That surface charge was found by doing E out minus E in. Yeah. See, so that's the Maxwell surface boundary I was saying. So I guess that worked. Okay, next question to classify. Long straight wire carries a steady current I. Let's try to draw this, I guess. Here's I. A rectangular conducting loop lies in the same plane as the wire. One side parallel. Oh, rectangular conducting loop. This is distance A. This is distance B. Find the net magnetic force on the loop and determine the direction of the force. Magnetic force? Hmm. Well, we didn't really do anything with magnetism. This is supposed to be electrostatics, but let's just try it anyway. U cross B. Um, Q. So I'm pretty sure that that's the same thing as saying VQ over DT, and then this would be like R across V. I mean, I'm not exactly sure. But I'm just guessing because we didn't really do the magnetic stuff, so I'm just kind of so just guessing, I guess. Find the magnetic force on the loop and determine the direction of the force. Um, so if we have so the current's going this direction. One second. Okay, I guess that's the other here. This is crazy. This chat window is massive. Okay, anyway, so if we have this current going this way, rectangular loop here, um, R is this way, the B field, where's the B field? But which topic is it? To be honest, it's not even in the topic list. So I guess I can ask James this question. Let's go to is that from the list? Okay, I'm looking at it. Oh, gosh. What the hell is going on? I think I have to go like way back here and just ask him for another question because he's losing track of the topics. Ah, yeah, this is a little better. So localized charge distribution is confined within a region much smaller than the observation distance r. Ah, what is happening? Everything is always so confusing. The localized charge distribution is confined within a region much smaller than the observation distance. I don't even know what this means. Okay, so here's the observation distance. Here's the charge distribution. Derive the leading two non-zero terms in the far field expansion. State the Okay, so the topics are multiple expansion, mm, and I guess that's probably it. I mean, okay, but the open and move is going to be, um, so set up V equals Q over R, or Q naught over R, Q1 over, I guess it's P cosine, over R squared, and then Q3 over R. And how do we know it's non-zero? Um, then we just do the charging intervals, and we keep the first two non-zero terms. Probably going to be the monopole and dipole. These things come with a half. Interesting. Monopole term is total charge. Dipole, quadrupole. Okay, I think this is correct. So let's go ahead and answer the next question. Make sure it combines numbers. Inside a spherical region, check it out. Region radius r, filled with a dielectric permittivity E. Polarization is given by PR, so dot in there, equals alpha r cosine theta r. Okay, determine the bound volume charge density, meaning this. Bound surface density. R equals R and compute the resulting electric potential as well. Separation variables. So, so clearly we've got topics of linear dielectrics, polarization, electric potential, separation variables, displacement, even differential calculus, I guess. And the opening move is going to be take derivatives, find bound charges, and use Laplace equation with separation variables to match the, well, we really only need to do this for R direction because we don't have anything else. For radial direction only, since symmetry is because of symmetry, and so then we have to match the polynomial to L. Looks like it's going to be L equals 1. I mean, I guess this is how we would do it. Bound charges. Oh, snap. This is wrong. This is P dot n hat is equal to the surface, bound surface charge. Okay. So then in that case, we would have no displacement. I mean, maybe, yeah, we have to do the boundary conditions later or something, but um, yeah, I'm pretty sure it was just for R. Good Lord. Solve Laplace radially. Yeah, okay. So that was that problem. Next question. Harder. Yep. This one. Two grounded infinite conducting plates. Look at that. Plus A, minus A, Q. Q is here. And then we have the axis right here. This is Z naught. This is V equals 0. Method of images. So, I mean, we have to like reflect this across here and then across to here. And then we have to start reflecting these other charges because it's going to go there. It's also going to go over here, and then this one's going to go like all the way over here. So we have infinite images. But he's telling us which topics to use, so it's kind of annoying. You have to ask for no hints. Determine the exact electrostatic potential VR everywhere between the plates. Reduce surface charge density on each plate. Force on the charge Q. Um, right, so here's the opening move, I guess. The net force on the charge Q. In order to do this, I think we have to place the plates with. No, I don't think so. I think we start with uh, a sum of V equals like the Q plus, I guess, Q over R minus Q over R. But we have to find some kind of pattern to do the Z images. It's gonna be like impossible to find that pattern, but maybe there's an easier way. Find the surface charge density, I have no idea. Net force is F equals QE at 0, 0, 0. You feel between the plates, then like E out minus E in. The net force is that, so we need net density. Start with the method of images pattern, infinite ladder of image charges. 2Na plus C naught, 2Na minus Z naught. See if I have that saved anywhere. Yeah, plus or minus 2NL, that's the one. This is really the secret right here. It's like the secret to solving it. Plus or minus 2NL. So then we sum it up, like I was saying. We can do this. If I have that saved anywhere. It's whatever. We come to the same conclusion by using E out minus E in. This is just minus conductor. Okay, okay, okay. All right, next question. I think we're good on this particular exercise, though. There's one more exercise I wanted to do.